In this video, we are going to learn about binary tree. So basically a binary tree is a tree data structure in which each node can have at most two child nodes. So that is a node can have zero child nodes, one or two child nodes actually. So that is if it is having one child node, it can be either left or right, or in the case of two child nodes, one will be left and one will be right child. So the node in the binary tree will be having a data and a pointer to a left child and also a pointer to a right child. So the basic operations that can be performed on the binary tree are insertion, deletion, searching and traversing. So here there are auxiliary operations that can be performed on the binary tree, that is nothing but finding the height of the tree, finding the level of the tree, finding the size of the entire tree. So first let us see how we can go with insertion in a binary tree in the level order. So this is a binary tree given to you. Now you are supposed to insert 16 in this. So what we will do is first we have to find the location which is available. Wherever it is empty, that to that location we are supposed to go. So for this we are going in the level order, that is BFS we are following. So right from 36 we are going to traverse. Using the queue we are going to perform this insertion operation. First traversing should be done, so then insertion can be done. So for identifying the first available position, we are traversing. So insert root into the queue. So we are going to insert 36 into the queue because front and rear are initialized to -1, and now when we are inserting it should be incremented, so both front and rear will be point to 36. Then we are going to make 36 as temp because we are going to delete 36 from the queue and insert left of 36 the into queue. So that is nothing but 9 we are going to insert. Then we are going to insert right of temp value, that is right of 36 also into the queue. So when you are inserting, rear should be incremented. So rear will be incremented, 27 will be inserted into the queue. Now your temp value will be updated to 9 because we are supposed to insert the child nodes of 9 into the queue. So delete 9 from the queue. So when you are deleting, front will be incremented. And now you are supposed to insert the left child of 9 into the queue. So when you are inserting, rear pointer should be incremented. Now insert 4 into the queue. Similarly, increment the rear pointer and insert 5 into the queue. Now the next value to be deleted from the queue is 27. So when you are deleting 27, it should be made as temp and front will be incremented. So you can see that 16 is inserted into the first available position because the left of 27 is null. So you will insert 16 in that particular location. Okay. The next one is creating a binary tree. So there is no tree at all to insert a particular element. So you are given a sequence and you are going to create a binary tree. So how it will be happening? So first 23 will be taken as a root, then 78 as a left of 23, 12 right of 23, 45 left of 78. Then next one is 56 right of 78, then 89 left of 12, 27 will be inserted as right child of 12. Then we are having 34 in the sequence. So 34 will be inserted as a left child of 45 and 90 as right child of 45. So you can see how the binary tree is constructed, and we can say that this is a complete binary tree. When you are creating a binary tree, it will be a complete binary tree actually. So complete binary tree is a tree which is nothing but it will be having a zero child nodes, or if it is having a single child, it should be a left child. It cannot be a right child. If it is having two child nodes, obviously it will be having both left and right child. So there is no problem. Let us see the deletion in the binary tree. So this is the given tree structure. Now what will happen? You are having the tree in this fashion. So if you want to delete 36, normally what is the procedure is the last node in the tree will be replacing the node what we are deleting. So if I want to delete 36, what will happen? 11 will be replacing 36. So this is how the tree will be looking like after deletion. In this, if you are deleting 4, what will happen? 16 should be replacing 4. So like this, the tree structure will be. Now let us see about the types of binary tree. Full binary tree. In the full binary tree, a node can have either 0 child nodes or 2 child nodes. But it cannot have a single child. Either left or right, it cannot have as a single child. So if you observe this particular example, 11 and 9 is having 2 child nodes. 27, 5 and 16 are having 0 child nodes. And also we can call them as leaf nodes here. So this full binary tree, we can also refer it as proper binary tree. Degenerate tree. In the case of degenerate tree, what will happen here is every node except the leaf nodes will be having a single child. Leaf node will not have any child nodes. So here the single child what it is existing, it can be either a left child or right child. There is no issue. But it should have only a single child. So here the degenerate tree can also be called as pathological tree. The next one is skewed binary tree. So two types will be there, that is left skewed and right skewed. So if every node except the leaf node is having the only left child, then we call it as a left skewed binary tree. Similarly, if every node in the tree except the leaf node is having only the right child, then we can call it as a right skewed binary tree. So I already specified about the complete binary tree. Now if you see here, 27 is having left child but no right child, so it is a complete binary tree. The rest of all is having either 0 child nodes or 2 child nodes. And if you see this particular tree structure, it is not having a left child but it is having a right child. So it is not a complete binary tree. Then perfect binary tree. So in the case of perfect binary tree, what will happen is every node except the leaf nodes, it has to have two child nodes. Only the leaf node cannot have any child nodes, but rest of all the nodes should have two child nodes. And also another condition is the leaf node should be at the same level. Then we can say it as perfect binary tree. Then balanced binary tree. So the difference between the left subtree and the right subtree can be 0 or 1. So if you consider the first example, we have already discussed about the height of the tree actually, right? So at any point of this particular tree structure in the example 1, the left subtree height and right subtree height is same. So we can say that it is balanced binary tree. Now, if you observe in the second example, the left subtree height is 2 and right subtree height is 1 in the case of 27. So, the difference is 1. So, again we can also call this example as balanced binary tree. Another case is this one, third example. So what is happening here? The balance factor of 9 is nothing but the left subtree height minus right subtree height is minus 1. So this also is balanced binary tree. So what we can say is the absolute value of the difference between the left subtree height and right subtree height can be either 0 or 1 in order to say the binary tree as balanced binary tree. Then binary search tree. In the case of binary search tree, the value of the left child should be less than the root node or parent node. Similarly, the value of the right child can be greater than the root or the parent node actually. So this is nothing but the binary search tree, and we will see binary search tree in detail in next video.